For those of you not familiar with NREL, we are part of the United States Department of Energy complex of national laboratories, and we focus on renewable energy and energy efficiency. The result, views, and opinions that I'll be sharing today in this presentation are those of the authors of this presentation alone and do not necessarily represent the views of the Department of Energy or the US government. This chart shows the US primary energy consumption by fuel. As you can see, roughly 80% of energy usage in 2019 came from fossil fuels, 37% from petroleum, 32% from natural gas, and 11% from coal, while the remaining 20% was split between renewables and nuclear. However, when we focus on the right-hand side part of this chart and we break down this energy consumption by sector, we see a significantly different story. The transportation sector, which is the first bar on the top right-hand side here, represents almost 30% of energy consumption in the United States. However, it is the least diversified energy demand sector, with over 90% of energy usage coming from petroleum. After over a century of petroleum dominance, however, major electrification trends are disrupting the transportation energy demand landscape. What we see here is the new electric vehicle car sales over the past few years in different regions of the world, borrowed from the global electric vehicle outlook of the International Energy Agency. As you can see, the global car fleet rapidly increased in the past years and exceeded 5.1 million vehicles in 2018. A dramatic increase in electric vehicle adoption compared to the previous years. After over a century of petroleum dominance, however, major electrification trends are disrupting the transportation energy demand landscape. What we see here is the new electric vehicle car sales over the past few years in different regions of the world, borrowed from the global electric vehicle outlook of the International Energy Agency. As you can see, the global car fleet rapidly increased in the past years and exceeded 5.1 million vehicles in 2018. A dramatic increase in electric vehicle adoption compared to the previous years. Vehicle electrification will have broad impact for the entire energy landscape. Plug-in electric vehicles in particular will greatly impact electricity demand, both in terms of how much electricity is consumed, as well as the load shapes, when and where electricity is used, and how electric vehicles can support system planning and operation. Keep in mind that electric vehicle charging patterns are highly uncertain and are determined by a number of different factors, including the charging infrastructure that is available to charge vehicles, the level and kind of vehicle adoption, electricity pricing, and other constraints that come from the electricity supply side. Vehicle electrification is at different stages in different countries, which have different opportunities when it comes to integrating electric vehicles with their power systems, as well as different opportunities exist to electrify different applications in transportations. So thinking about personally owned car or light-duty trucks, or ride-hailing vehicles, or school and transit buses and trucks. All these different transportation applications offer different opportunities for electrification and then in turn impact the power system in different ways. Understanding different opportunities for transportation electrification and how they impact the power system is really the first step to successfully integrate transport and power system of the future. What would be the impact of electric vehicles on the overall system electricity consumption? What we see in this chart here are results from a study called Electrification Future Studies, EFS, that we've been conducting at NREL for the past couple of years. All the reports and the data associated with the study are publicly available on our website, nrel.gov/EFS. And what we see here is how the electricity consumption has evolved over time in historical years, broken down by sectors, so industrial in red, residential building in orange, and commercial buildings in green, and a very tiny small sliver for transportation in blue. Transportation accounts for roughly 0.3% of electricity consumption today, so it's really hard to see. On the right-hand side of this chart, when we start projecting into the future, we have three scenarios that we articulate: reference, medium, and high, where these names refer to the level of electrification that we project in these different scenarios. So focusing on our high electrification scenario, so think about the future where electrified technology achieve widespread success across all sectors. The one change that really is evident from this chart is the role of transportation. In 2050, in this scenario, 76% of every mile that is driven on road, including light-duty vehicle as well as commercial vehicle, buses and trucks, is driven on electricity. So there is a very high success for vehicle electrification and adoption of electric vehicles. And this translates in an electricity consumption of 23%. So 23% of all the electricity that is consumed in this scenario in 2050 goes to transportation, up from 0.3% today. So as you can see, the transportation sector goes from playing a virtually inexistent role from the power system perspective to being roughly a quarter of overall demand in 2050. One of the questions that we are often asked is whether high level of electric vehicle adoption will, quote unquote, break the grid. To try and answer this question, I'm borrowing here a figure from a recent report published by US Drive a few months ago, where we compared the expansion that the power system in the United States experienced over the past 20 years compared to the number of vehicles that expansion could have supported. So what you see here in this dark blue line is the power generation capacity expansion that happened in the power system, plotted in terms of equivalent number of electric vehicles that could have been supported by this historical capacity expansion. What we conclude is that based on historical growth rate, sufficient energy generation and generation capacity is expected to be available to support a growing light-duty electric vehicle fleet. However, these results do not consider operations requirements of the bulk power systems, nor they focus on distribution and transmission capacity that could be required to support this electric vehicle adoption. And these are some of the aspects that I'm going to talk about in the next slides. When we think about the impact of electric vehicle charging on the total system power demand, it's important to understand that EV charging can look significantly different and require different level of charging infrastructure if vehicles are charged at different locations or at different times. What you see here on the left-hand side is a situation, a scenario in which we imagine that electric vehicle charging is simply a scale-up of the existing load from other sectors. However, we know that electric vehicle charging happens in different ways than power consumption from other end uses. And this adds a complexity. Electric vehicle charging is not just going to scale up power demand, it's also going to change the shape of power consumption. What you see on the right-hand side of this chart here are two alternative possible scenarios of how electric vehicle charging might impact the overall load shape. One assumes predominant home charging of electric vehicles, and one assumes predominant workplace charging of electric vehicles. As you can see, the area under all these curves is equivalent. We are using the same amount of electricity. We are supporting the same fleet of electric vehicles driven in the same way. However, the peak overall power consumption and the shape, the ramping requirements for that consumption are significantly different in these different cases. Moreover, electric vehicle charging is intrinsically flexible. Vehicle batteries are not fully used every day, and vehicles can charge at different times and at different locations. This is particularly important as the power system is also evolving. Historically, power system generation has followed demand, and power plants have been dispatched so that demand could be accommodated. However, with the great adoption of variable renewable energy sources like solar and wind, the flexibility on the supply side is decreasing. Power can only be produced from PVs when the sun is shining and from wind turbines when the wind is blowing. This really increases the value of flexibility on the demand side. If demand can be flexible and accommodate requirements and constraints from the supply side, the system can be operated in a more efficient and effective way for everyone. This is what you see here represented in this chart on the right. Flexible electric vehicle charging can really complement the net load to help shave peaks in power demand, fill valleys in power consumption, help mitigate ramping constraints, and support the operation of the power grid, including reducing curtailment of renewable resources, as well as providing distributed services like reserve and contingency. This graphic from a recent IRENA report summarizes the potential range of flexibility services that can be provided by electric vehicles, breaking it down between system flexibility and local flexibility that we're going to talk about in the next couple of slides. Just to give you an example about the value of flexible charging, some colleagues of mine at NREL produced a study published a couple of years ago on optimal charging of electric vehicles in California. They considered 3 million electric vehicles in California in 2030, and these vehicles are responsible for would be responsible for approximately 4% of the total load. However, flexible charging of these vehicles could reduce electricity production costs by up to 7.6%. And this is electricity production cost experienced by all consumers, not just electric vehicles owners. By exploiting flexible charging, electric vehicles owners could actually reduce their charging costs by up to 80% in this study. Focusing on local perspective, residential charging of electric vehicles represents a significant increase in household electricity consumption, and this increase might require upgrades of the household electrical system, and unless it's properly managed, it might also lead to exceeding the maximum power that can be supported by distribution systems, especially for legacy infrastructure and during times of high electricity utilization. What these charts show here is the average load factor of a distribution transformer connected to a handful of households in the Midwest region of the United States. The load factor is the ratio between the power that is actually drawn from the transformer and the nominal capacity of the transformer. As you can see, in the case where there are no electric vehicles, the load factor is consistently below 1, meaning that the transformer is never required to operate at the power that is higher than its nominal capacity. On the other hand, as electric vehicles are introduced, the load factor is pushed more and more above the 1 threshold, implying that distribution transformer might require to be upgraded. The impact of electric vehicle charging on distribution transformer is particularly affected by clustering effects. While 100% electric vehicle market adoption is a very high adoption level overall, it might make sense in that electric vehicles are often adopted at high market shares in specific areas. These clustering effects in vehicle adoption are driven both by socioeconomics and demographics that tend to concentrate in certain areas, as well as by neighborhood effects. Effective planning, smart charging of electric vehicles, as well as potentially the use of distributed energy storage can all help to cope with these issues in integrating electric vehicle charging with distribution networks. Thinking about vehicle electrification and its impact on energy system and the power system in particular, here I wanted to touch on a couple of takeaway points. First of all, electrification trends are really disrupting the transportation energy demand landscape and might fundamentally change the amount and the way that we use energy in transportation. Smart charging of electric vehicles creates great opportunities to support the evolution of the power system and facilitate the integration of variable renewable energy resources. However, this potential needs to be assessed reasonably given that flexibility will likely be secondary to mobility service demands. Electric vehicles are purchased to satisfy mobility needs first. Within the boundaries of satisfying these mobility needs, electric vehicle can also provide flexible charging and services to the grid, but it's always important when assessing the value of flexible charging and the ability of electric vehicles to provide this flexibility to consider mobility needs first. Integrating electric vehicle charging with distribution systems and some of the related issues that we talked about in the previous slides is geographically and use case specific. It's hard to draw general conclusions about the impact of electric vehicle on distribution system because these implications and the impacts will change on a case by case basis. However, one open question that remains to be assessed is that are the trade-off between bulk power and distribution system needs when it comes to load reshaping. Think, for example, about alignment of electric vehicle charging with solar production. You know, from a bulk power system perspective, concentrating EV charging during the hours of the day in which solar electricity is widely available is a good outcome, but this also implies a load concentration during the hottest hour of the day that might pose some problems from distribution networks. These trade-offs between bulk power system and distribution remain to be answered. Finally, multiple benefits of system integration across different sectors require closer coordination across ministries for governance, research and development efforts and analysis, as well as planning and industry. As the transportation sector transitions away from fossil fuels and petroleum, and we see more widespread use of electrification, there are great opportunities to think about the planning and operation of the transportation and the power systems in a coordinated manner that would benefit both the power and the transportation system. For those of you interested in more details, here is a list of references for works that have informed and have been used in the slides that we discussed today.